chemical engineering and even chemistry, right? And also physics. So, frankly speaking, in Korea, on these days, chemical engineering, and most of the engineering school, the engineering students wanted to be chemical engineer because we can get a lot of money. also, we can do some science. Even the part of the students go to the medical school after undergraduate or after graduate. So, in my personal opinion, chemical engineering field is one of the best major in the engineering and the science field. So, do you agree about that? Okay, so somehow you should be very boring because you already that sitting in a very long time here. I like to travel very much, to me. So I traveled many Asian countries, and I traveled many European countries, and also I studied in the United States, and I stayed 6 years over there. In my personal opinion, Asian country has a lot of different stuff compared to the European country and the United States. For example, even in China, I don't know whether you have experience of travel to different areas except for Qingdao and Beijing, Shanghai, and Hangzhou. And if you, in my personal opinion, okay, I think there are many Chinese students over here. In my personal opinion, if you have time, it will be really nice to go inside of the China a little bit, like central area. That's really Chinese stuff. Also, I recommend the Vietnam or the Cambodia. That's really something different from European countries. There are many hidden places, so you can take a look at, and you can feel many smells of there. So also, Korea is also a good country. I hope you have a chance to visit Korea. Probably in the future, I have this kind of session to Korea. So Korea, even though it is a very small country, we have a very nice mountain and ocean. So I really welcome to visit Korea and send an email to me. Okay. Okay, today I'm going to talk about molecular assembly. I heard from Ivan that your major is really broad. So in the morning, I will just briefly describe what is the molecular assembly, and I will show you some examples of it. So this is the outline. I will talk about what is a self-assembly nanostructure, and I will show two examples. One is surfactant self-assembly, one of the typical examples of the self-assembly to understand more physics and the chemistry of the self-assembly system. So lecture 3 will be a block component for self-assembly. It is related to some part of physics, and also it is associated with chemistry as well. Maybe tomorrow I will give a talk on the self-assembly for some application of the photonics and electro-optic photonics using self-assembly building block. Why we study self-assembly nanostructure? So I will show many examples first time, and I will identify definition and etc. Self-assembly nanostructure provide the first high density stuff for anything. So this is an example of a high density data storage made from block copolymer self-assembly system. So, as you know, like the hard disk capacity, data storage capacity is about 1 gigabyte per inch square. It is still, trouble, and many scientists wanted to make a bigger size for their capacity. So that's one of the way to produce high density of the data storage. And starting from block polymer self-assembly, we could fabricate this kind of the high density data storage. This is example of short CRPD, which is the magnetic materials. Starting from those kind of stuff, you could make this kind of high density storage, which is about 1 terabyte per inch scale. Actually, as far as I know, a Japanese company, which is Toyota, I think, they already developed high density data storage using block coupler systems. And they made like the disk, and they announced it to IEEE symposiums. But they said the problem is the electronics. That's not. But electronics sensing system does not follow this kind of the high density storage. But again, what I wanted to focus on is that self-assembling system provided this kind of high density the storage. So why self-assembling nanostructure? So answer one is it provides high density storage. And the other, this was also we studied from block polymer self-assembly. And we incorporated some kind of the biomolecules inside of the block polymer parts. And we checked stability and the sensitivity of biomaterials. And compared to just a non-structured self-assembly substrate provide a more stable biosystems. So answer two may be, okay, self-assembly system give us high sensitivity or high selectivity or highly stable biosubstrate. So that's the other case. Also, why the self-assembly nanostructure? It can provide formation of the other material. Like starting from self-assembling nanostructure, you can fabricate the other organics or the other inorganics. So, for example, this is made by supramolecular self-assembly. So this is golden nanoparticles provided by supramolecular self-assemblies. So using molecular self-assembly, you can provide nanowire or different stuff of the nano-shaped inorganic metal, ceramics, something like that. So answer three is okay. Self-assembling nanostructure materials can provide formation of other inorganics or other shapes of materials. That's so, for example, starting from block polymer micelle, you can produce this kind of the golden dust. Okay. Probably it's where. So also self-assembling system. This is many layer line made by supramolecular columnar liquid crystals. So then it could. So if we starting from this material, and if we use templates of this material, then we can make like the nanowire stuff, something like that. So this is another reason why we studied the self-assembly method. Okay, and the other purpose for studying the self-assembling material is that self-assembly material is kind of templates to give orientation of the organic or inorganics. So using the self-assembly material, you can orient any kind of material like the parallel direction or vertical direction. Okay. So this is one of the examples. So usually a carbon nanotube, in the case of carbon nanotube, one of the critical issues is the vertical alignment of the carbon nanotube without any direct growth. So there are many ways, but some self-assembly system, like if you self-assemble, this is colloidal self-assembly, and if you deposit some carbon nanotube material, they insert it into intersect of the between so the within the colloidal self-assembly, they ring to the colloidal and showing something like alignment. So self-assembly give alignment of the other object. So that's one of the also big purpose of the self-assembly system. Also, self-assembling materials. So if you control structure of any system, that can provide, enhance some mechanical property as well. Okay, so this is another example. Actually, I collaborate with some professor of mechanical engineering. So he also is only interested in money. And okay, this is carbon steel plate, and this is polymer composite. So conventional method is just the brushing with the sandpaper to enhance adhesion between polymer and the metallic sheet. So, but however, in order to make a more systematic or much more enhanced to mechanical property, or enhancing something like adhesion property, we may have to use periodic nanostructure on the surface of the carbon steel. Okay, even in the liquid crystal community, as you know, I think very well, we do lobbying to for the display to align the nematic, liquid crystal with some surface anchors, right? But even in that case, that is not very systematic. So nowadays, many people is investigating, providing the nanostructure on the surface to align the, liquid crystal molecule instead of just the lobbing. So that's one of the purpose. So when we put this kind of nanostructure on carbon steel plates, as you compare, I don't think you see very well. This is like a mirror polishing. Sandpaper is the other way. And when we provide some nanostructure on the carbon steel surface, adhesion property is really enhanced. So, if you try molecular assembling nanostructure to any surface, there are some possibility to enhance even mechanical property. So there are many advantages of that, right? So first thing is high data storage and very stable bio sensitivity and stability and the control orientation, okay, on the formation of the other inorganic material, also enhance the mechanical property, okay. Also, this is another stuff, and this is energy device. So as you know very well, polymer heterojunction solar cell device, which is most famous one is P3HC the PCBM systems. So the efficiency is about 3 point something on this. And if you give some nanostructure pattern on the surface of the polymer, that increase surface area. Also, they can the morphology. They can change morphology of the P3HC PCBM systems. So when you compare without any, this kind of the periodic nanostructure, and with periodic nanostructure, in the presence of the nanostructure, it substantially increase the energy efficiency also. So there are many people who are working on providing surface nanostructure on the surface of the polymer junction, or middle side, or in bottom, to increase surface area as well as changing morphology of system. So according to this result, yes, the nanostructure, self-assembly nanostructure, can increase energy properties. Okay, so and this is the system of the project. And this is another example. And the conventional bio device, fluorescence-based bio device, use just a substrate like glass substrate, quartz substrate, whatever. And if you put something like high structure of the like a gold nanoparticle or even the silver nanoparticle on glass substrate, can increase significantly fluorescence signal. Okay, based on metal enhanced fluorescence effect. So which is coupling between localized surface plasma effect. So I will show you maybe tomorrow of these examples why we have to self-assembly. So let me summarize it. Why nanostructure? First, it can increase high storage density. So as I show you, okay, biosensing stability, sensing ability, and the selectivity and the stability as well. Also, optoelectronic property, I show you already. Energy properties, right? So when we make some surface nanopattern on the polymer junction system, that increase efficiency. And the mechanical property, like adhesion property or right property, whatever. And the formation of organic and inorganic, starting from self-assembling nanotemplate, you can produce nanowire, nanoparticle, other nano-shaped materials. And also, self-assembling nanostructure can give you alignment of organic and inorganic. So if you already aligned nanostructure, if you use, then you can align other objects which you want to align. That is purpose why we have to study nanostructure. And particularly self-assembly nanostructure give you a relatively simple way because compared to the other top-down approach, because it is really simple, and you can produce it with a low cost, very low cost. That's very interesting in chemical engineering. So, and also, so that's why in this class you have to know what is molecular assembly. Okay. So let me now a little go inside of the molecular assembly. Okay. There are some definition is different in chemistry, biology, and physics. In chemistry, molecular assembly, I did not copy his presentation. This is my own stuff. I never know. In chemistry, they said the well-defined structure, spontaneous from composed by non-covalent body. That's so non-covalent bond is important in the case. In biological point of view, assembly is defined as spontaneous building of complex structures on the adequate environmental condition on the basis of respective molecular properties. I don't see very different. In physics, they say spontaneous formation of new three-dimensional and temporal structure in complex system, which result from the cooperative effect of the partial system. I mean, that's feel a little headache, but meaning is the same. Without any covalent bond, they form spontaneously. Okay, that's different from like a polymer system, which is bonded by a covalent. So this is one of the good example to understand the self-assembled building block. So I use very often this system. As you know, this is tobacco mosaic virus, which is kind of the organism. Okay. But when you see the detail of the structure of the TMV, that is composed of a single RNA, okay, RNA, and also they composed of the many DNA, like 2,130 DNA, is assembling by some environmental condition provide this TMV structure. So when you think of the RNA molecule and the DNA molecule, actually my major is polymer. I mean, the undergraduate school is the chemical engineering, but I got a PhD in the polymer. In the polymeric sense of view, DNA and the RNA is just a neighborhood of like your shirts, like that, like the nylon. That's a very similar chemistry of them. So this is a polymer. Protein is polymer and RNA is polymer. So they don't have any life, right? They don't have any life. That's just a polymer, like your shirt, your shirt. And but when they, for some reason, when they self-assemble into TMV virus, they can provide something like life system. So many self-assembling chemists and physicists, one of the main goal is to find out what is behind of the this mechanism. Okay, because polymer is just nothing actually. They are just like the nylon-like the structures. But when they do the self-assemble, it gives a lot of ability, even the non-organism into organism. Okay, so this is a lecture of Clark. He published in the Argumente, and this is a self-assembly. They spontaneously assemble based on whatever, based on molecular interaction, based on molecular shape, based on temperature, based on concentration, pH, some parameters. Okay, this is self-assembly. So that means that without self-assembly, it does not give any function. And it does not give any clear function. But with the self-assembly, for some reason, they give some structures and functions. That's the important significance of the self-assembling system. So when you think of the surfactant system, there are many phases depending on concentration and the temperature. For CMC, below CMC, it is just nothing. That's just a surfactant of the isolated molecule. But when it form to self-assemble into micelle phase, it gives a lot of function to us, like drug delivery system or the other microstructures. So that's the self-assembly. Okay, and this is a schematic, actually classification of the self-assembly building block. This is similar to liquid crystal, and that can be divided into molecular shape, molecular ordering, and the nature of phase transition and types of the mesogenic materials. And in the case of molecular shape, we can divide it into like board-like, node-like, taper-like. This is similar to liquid crystal. This is like banana shape. And when they self-assemble into some region, in some case they form the micelle vesicle phase, nematic, cholesteric, lamellar phase, or the other two-dimensional or three-dimensional structures. Nature phase transition is mostly based on thermotropy, which is dependent on temperature. When you control temperature, this shape of the molecule are self-assembled into this structure. Okay, and the lyotropic is dependent on concentration. So when you control the surfactant phase, one of the typical system, when you control surfactants, some shape of the molecule can organize into this structure based on molecular interaction and the molecular shape. I will show you later. And there are two different materials. One is a small molecule, the other is polymer. So I hope you to remember this classification. So if you do not understand, just remember. Okay, just keep memory. But later it gives you a lot of systematic organization of the you are taking, I think. And but when you see this classification, you can get a lot of insights of the nanostructure. For example, like load shape of the molecule, like that one, is generally form into this kind of nematic, cholestic, the lamellar phase, something like this, right? Because of the shape. If there is some molecular interaction with the other molecule, they easily form to those kinds of structures. It is very hard to form the micelle phase because of the shape, right? But the taper-like shape, think of the taper-like shape. Like the logo, if you have a lot of this type of logo in your home, what is the most easiest structure to use this logo? Probably there will be something like that, right? That's very, very easy to make it, starting from your individual logo. So that is hexagonal system, like the cylindrical system. So if you get insights about the molecular shape of the whatever system is, then you can expect what types of structure is formed. What about this disc-like? Okay, if you have the disc-like some logo in your home, so what do you expect of the final structure? Is it this micelle vesicle nematic? That's also the cylindrical system, right? You can just attach with a glue, something like that, and make it. So what I want to point out is when you see any object, which is either spherical or like this rod-like or triangular, and this kind of tab-shaped molecule or object, whatever, and the disc-like or something like different. But you have to think of that. That molecular assembly is almost the same as logo, self-assembly of the logo. So molecular system is not much different from your the logo system. So many percent, majority of these types of molecule form into this kind of column or nematics, something like that. So okay, this is you have to get insight of that. And as for material, as far as material is concerned, it can be divided into amphiphilic and non-amphiphilic. So in the case of amphiphilic, maybe the surfactant and the biomolecule. Synthetic supramolecule is in the actual boundary of the amphiphilic and non-amphiphilic. Some of the synthetic supramolecules included in the amphiphilic, but the other is not. In non-amphiphilic, block polymer is one of the typical examples. But there is also amphiphilic block polymer. But in general case, block polymer concept is based on microphase separation between two disliked polymers. But there is also the amphiphilic block polymer, so conventional block polymer. Colloidal assembly is one of the examples of the non-amphiphilic molecular assembly. But again, there is example of amphiphilic colloidal assembly as well. But this is just a general self-assembly materials. And again, when the self-assembly, when you observe one self-assembly material, and you have to, one of the goal is you have to expect final structure. Okay, there are two very important parameters. One is again the molecular interaction. The other is molecular shape. Molecular interaction, I think you know very well. There are many different molecular interactions. Covalent bond, ionic bond, metallic bond, van der Waals bond. So, but all of the combination above is just the general system. And the thermal energy, also you have to remember, at room temperature is this value. And so covalent bond is, but some system is different. In some system, ionic interaction is a little higher than covalent bond, but in general, covalent bond is about in this value, 5 electron volt. And the ionic is 1 to 3, metallic is 0.5. Van der Waals is 0.01 to 0.1. So, if the self-assembling material has a very strong molecular interaction in between, or between the structures or between the molecule, then you can have a more complicated structure. Okay, so that's depending on you have to recombine your logo. So that's kind of the molecular interaction. So if stronger, in general, stronger molecular interaction, it just provides high order system. Okay, if it is not high order, then it is highly aggregated. Okay, so covalent is just like a polymer chain. So in van der Waals interaction, you can also divide it into 3, right? Dipole interaction, induced dipole interaction, and induced dipole interaction. So in order to make a strong interaction of the different molecular system, it will be better to provide dipole interaction, which is more stronger than induced dipole interaction or induced dipole interaction. So people say that there are a lot of arguments between hydrogen bonding and van der Waals force. So what do you think? So between van der Waals force and hydrogen bonding, van der Waals force is included in, the hydrogen bonding attraction is included in the van der Waals force. So what do you think? The chemist. Yeah. For people said van der Waals for hydrogen bonding is it is some argument about one of the strong dipole the interaction case. So in order to make high structures, highly ordered structure, it is easy for you to provide a stronger interaction rather than weaker interaction. Like in this type of interaction, you can provide it. Then it is better to provide like a hydrogen bonding inside or outside whatever the molecules of them. And the other, okay, for example, okay, this is the example of the molecular interactions. I will show you later in detail. This is block copolymer. Okay, block copolymer. Block copolymer is two dislike polymer is covalently attached each other, and they go to microphase separately. And depending on their fraction and their volume fraction, they form variety of structures, lamellar, columnar, cubic, and even more structures, more complicated structures. But when you see the block copolymer, in the point of the molecular interaction point of view, so what is the interaction in the here? Covalent bond, right? Covalent bond. So okay, this is a covalent bond which is very, very strong. And in order to form the lamellar systems about here, okay, this is block copolymer, and which is connected to by the covalent bond of the two discrete polymer, which is very, very strong. And in order to make lamellar phase, so this molecule has interaction to the other block copolymer, which is van der Waals interaction. Okay, so if the van der Waals interaction is very, very strong, it has more probability to lamella is getting highly ordered rather than just the undulated lamella. Okay, so this covalent bond, and this is mostly, but you can control the surface, but mostly it is interconnected by van der Waals interaction. That's why they generated this kind of lamellar system. Without any van der Waals interaction, that just can be individual lamella. So that's why this kind of molecular interaction in between the blockable system, okay, is important. So here, molecular interaction again determine this kind of morphology. Also, shape is very, very important. So when you think of the this is A block, this is B block, and if the length is the same as if this AB length is same, in this case the fraction is different, but you can think of the like a temple shape, the temple shape, the tempered shape instead of just a linear. Then again, you have a lot of probability to form cylindrical phase. So if it is more, curvature like that, it usually forms into like a conical stuff. So this kind of molecular shape and the molecular interaction is very, very important to generate this kind of variety of structure. This is key factor. And the supramolecular dendrimer is also saying, I told you shape and the molecular interaction determine their final structures. So here, tab-shaped molecule is easy to form this kind of cylinder, like a logo again. So if you attach both molecules, you need some interaction, molecular interaction. So this molecule should interact to the other molecule like that. So this is molecular interaction. So the molecular interaction is very high, then it is easy to form like a crystal shape, three-dimensional order instead of one or two-dimensional order. Okay. So in colloidal system, usually colloidal system, the shape is already decided, which is sphere, right? In the case sphere, I think what's the easiest formation of the structure is like FCC and some HCP, something like that, right? Because it is packing parameter is higher than the other molecule. But in general, it is connected by van der Waals interaction. But if you create some surface of a colloidal surface, you can change it, like electrostatic interaction, something like that. But in general, it is determined by van der Waals interaction. Surfactant is the same. And I say also, the molecular shape is very important. Again, this kind of tape form, the tape shape determine is to form cylindrical shape, and if it's like the cone shape, it is easy to form sphere shape. So I would like to stress that when you see any object or any chemical or any molecule, take a look at very carefully, then you can expect final structures. Okay, so when you see molecule very carefully, it looks like if it looks like a sphere, the final structure probably form into like a sphere type, which is cubic structure or BCC, HCP, whatever. And if your molecule, who designed by chemistry, is a rod-like shape, and there is some functional group inside or outside of chemistry, you can expect what will be a final structure of your system. So if it is like some rod shape, but in end group, if there is a strong dipole moments functional group, it is very easy to packing very well, which form highly ordered symmetries, for example. So just take a look at very carefully first time your chemical or your object first, then you can expect everything. That's molecular sampling. Okay. Okay, so we will break because so next is the lecture 2. Okay.
Questions, please. Are there some questions?
So education.
If not, we will reconvene in 10 minutes from now.
Beijing and Shanghai. Beijing maybe three times, and Shanghai 3 times. But this time I visited in Hangzhou, and so this is my first visit. And compared to several years ago, when I see the Chinese city, automobile car is much changed. So several years ago, most of the taxi and the car was like made of the Japanese, I think mostly. But now the situation seems to be changed a lot. I see a lot of German car, Volkswagen, yeah. Because I'm very interested in the car. So, and also I see like Audi, something, Benz, BMW over here, Honda, Hyundai, and Toyota, something like that. So actually, I tried the test drive of most of the car, very recently, And I tested the Benz E-Class. You know that? Just the test drive. You know, I do not have a lot of money. And I tested the BMW 5 Series. Also, I tested the, do you know the Infinity? Infinity? That's very rare in the Infinity here in China, I think. But I tested the Infinity and Honda Accord, new Honda Accord. And I tested the Volkswagen CC, Volkswagen Passat CC. That's a new car actually, born in the 2009. That's kind of the sports setup. Also, I tested Hyundai Genesis. Probably you don't know Hyundai Genesis. And I also tested Nissan Altima. And tested Volvo S80. So what do you like? What do you like among the car I told you? In my personal opinion, actually I like like a speed driving. So when I tested it, I think Infinity is okay. Infinity, I tried the Infinity. I'm not Japanese, okay? I'm Korean. In my personal opinion, Infinity G37 or G35 is really nice car. So when I test drive with a really high speed, it seems to be really stable. Also, in my personal opinion, in my case, BMW is also okay. So when I test drive BMW in highway, BMW seems to be something different from the other car. Like a Benz. Benz and BMW is something different. So when I test drive with high speed, the center of mass of the car is, I think, on the bottom, rather than the middle side. So that when I drive fast of the BMW, it is very stable. Okay, and the other car, Hyundai, which is my country. Hyundai, I think, do you know the Genesis? Genesis is a new car, which is constructed recently and competed with Lexus. And I also tested, the Lexus. Competed with two Lexus and Infiniti M series, something like that. So when I tested, Genesis is really nice car. That's not because I'm Korean. That's really nice car. Please test drive Genesis. Okay. Price is cheaper than the Lexus ES series. So I'm thinking of buying Genesis, Hyundai Genesis. Okay. So because I just talking about my hobby. Okay. So number one hobby is tennis. So, okay. So now I described briefly what is self-assembly and why we have to study self-assembly in first place. I think the mic is better. Okay. For music sound, okay. One more thing. For music sound, I think Genesis is best. Okay. Pretty testy. particularly high grade like VH series. So I will try one more. And on second class, I will show you two sample assembly examples. One is surfactants. That is really fundamental. The other is block complement self-assembly. I think if you understand those two systems, I think you will get much more insights about the molecular self-assembly. So there are many self-assembly systems, but this is two typical self-assembly systems. So I will go a little deeper inside of the two self-assembly systems. Okay, lecture 2 is surfactant self-assembly, which is really famous material. It is in everywhere. So, okay, this is phase diagram of 3 components. One is surfactant. This is water, oil. Even we don't know. Still we don't know how much structure exists in this simple 3 phase. So, there are many phases, like here, spherical micelle, cylindrical micelle, something unknown phase, and hexagonal phase, cubic, lamellar, cubic, inverted hexagonal, inverted micelle. Even in your here, some gyroid phase, something like exists, or many unknown phases. There are many unknown phases in the surfactant system. Because compared to the block polymer system, microstructure or nanostructure of surfactants is much more difficult than the other sample assembly system, even though surfactant is very conventional material. That's because of surfactant microstructure is difficult to characterize, very difficult to characterize. This is mostly lyotropic system. So lyotropic molecular assembly is very tough to analyze of the structure compared to a thermotropic system. Because there is also, solvent or water, we have to keep the constant of the concentration of the solution, right? So that's very difficult. Even we don't know. Even in the Langmuir paper on these days, some people publish U-phase diagram, like a surfactant 1, surfactant 2, and just water. And even they don't know of a full phase diagram. So if you draw full phase diagram, it is just easy to publish Langmuir or higher the effect paper. But there are a lot of guess, a lot of assumption for nanostructure or microstructure surfactant system. Okay.
Question: this particular diagram, was it for a particular ternary surfactant system?
No, it's just a general. Yeah, that's just a general. If we choose a surfactant, particular surfactant is much more complicated. So we have to find out with my eyes or with the spectroscopy or direct visualization and some scattering tools. Even we have to use the rheological mapping of them to identify the structure of the surfactant system. So as you know, surfactant molecule is just composed of hydrophilic part, short bulky head, and hydrophobic part. Typically hydrocarbon chain of length 8 to 20 carbon atom. So that's divided into single-tailed surfactants and double-tailed surfactants. Single-tailed includes anionic, cationic, non-ionic, G-ionic. G-ionic contain both. Okay. And double-tailed, typically in the lipid. And self-assemble this molecule, surfactant self-assemble into monolayer, bilayer, or multilayer based on molecular shape. I already told you. And the molecular interaction, also that's most important parameter, two parameters to determine final structure. also as a function of concentration, temperature, pH, salt, or whatever, okay, etc. And the phospholipid is just the fatty acid derived surfactant. Okay, just two tails of surfactant. And here there are two microstructure arguments, which is also applied to the other molecular assembly. One is a microstructure argument suggested by Jacob in UC Santa Barbara. And what he suggests is packing parameter, packing argument, packing parameter, which is associated with the molecular shape, actually, determine the structure, microstructure of the surfactant. For example, he introduced the packing parameter, which is P, is divided by V, is volume of hydrocarbon tail, divided by A is area on the surface of the aggregate, the multiplied L, okay, L is tail maximum effective length over here. So packing parameter can determine final structure of this molecule, this surfactant molecule assembly. And when the packing parameter P is less than 1.3, it usually forms into spherical micelle. Okay, when it is in between in here, that forms into rod-like micelle, which is called the other word worm-like micelle, cylindrical micelle, rod micelle is the same. And when packing parameter is in between 0.5 to 1, it forms into vesicle phase. The vesicle phase is close to the bilayer. And when packing parameter is 1, the form into the lamella. So same as in like a bronchopolar system. Okay, so this kind of the packing parameter determine this kind of the structures. Okay, so conical molecule usually form into spherical micelle like that, and the cylindrical molecule, like this molecule, this molecule usually forms the lamella. That's really depends on shape, right? Wedge shape the molecule is inverted molecule. Wedge is just actually the reverse of that. Okay. So shape of the surfactant aggregate can be anticipated based on packing of simple molecular shape. So in molecular assembly, again, even in polymer, colloidal assembly, supramolecular assembly, surfactant, whatever, you have to keep in mind the molecular shape first. And then you have to think of the molecular interaction the next. So block copolymer is same. When the volume ratio of the block copolymer determine packing parameter as well. So when it is like A and the B ratio is the same, this is the shape is similar to this kind of the cylinder. Okay. But when the fraction of the volume and the A, B is different, when it moves to shape is different, forming different structures. So, and also the other argument, which is the surface curvature argument, probably the physicists know very well. According to the free energy is function of the K, which is bending constant, with the Gaussian constant. Okay, K is curvature modulus, bending modulus, and the K bar is saddle-splitting modulus. So in here, the spontaneous curvature is quite important. Probably as you know, like the flat paper, spontaneous curvature. Okay, I will. Spontaneous curvature is minimum energy curvature. Right? So in first parameter, Jacobs described by packing parameter for determining final structure, but here the surface curvature argument is also important. So when that's really depends on the topology or geometry of your system. So for example, this paper wanted to be flat, okay? Wanted to be flat. This is minimum energy of the this architecture, right? So what is the spontaneous curvature? Just spontaneous curvature should be infinite, right? Because this wanted to be flat. But when the molecule, like this kind of this shape of molecule, but they have their original spontaneous curvature. Okay, they don't want it to be flat. They have any particular spontaneous curvature, which is minimum energy curvature, right? So, but based on the concept, if the polar head of the surfactant molecule is larger than on polar tail, then if we pull to pigment here, and they have any particular spontaneous curvature, so they, just the flat area is now still the minimum energy. This maybe is the minimum energy for this type of molecule. Head of the surfactant molecule is larger than a tail. Probably this shape is minimum energy curvature. Okay, this is minimum energy. So and they have some particular structure which is a spherical micelle. When the tail and the head are almost same size, like that. So H0 is 0, planar or satellite that forms to lamella, or the muscle lamella or the cubic crystal. And if the head is smaller to tails, and the surfactant packed into here with the water core inside, and they have also some particular spontaneous curvature like that, right? So in this case, it goes to this is the spontaneous curvature, which is minimum energy. But in here, the head is smaller than tail, that this is spontaneous curvature, which is minimum energy. So generally, non-ionic surfactants H0 decrease with increasing temperature and opposite to non-ionic. So spontaneous curvature of phospholipid has two-tailed something like structure, which is head group, and then the tail group, so which looks like some flat cylinder. Okay, so they want it to be flat, which means spontaneous curvature is 0. Okay, this is just they want it to be flat based on the molecular topology, geometry. And so spontaneous curvature of phospholipid is close to 0, like that. They want it just flat, okay? And they usually paint the bilayer forming the lamella, the liquid crystal lamella phase. And if the bending constant, you have to also the bending constant. If the bending constant is right over to the KBT, KB is the Boltzmann constant, and that's the temperature. The molecule is very rigid, and the more ordered phase, liquid crystal phase is favored. And but bending constant is close to highly disordered phase. They go to spontaneous, like by continuous micro emulsion, or highly swollen the lamella phase. So when you take a look at this equation, all molecule has minimum energy. So like that. And in order to bend of this always the molecule starting from spontaneous curvature, okay, which is minimum energy. So in order to bend this molecule, we need some energy, right? Depending on bending constant or Gaussian Sanders-Sperry modulus. So sometimes we starting from spontaneous curvature, we need some curve, or we need something like twister, something like that. So that's why the molecular elasticity is important to determine this kind of stuff. So that's really based on molecular shape. And also, there are another physics in behind bilayer, which is bilayer interaction. So in bilayer, surfactant form in the bilayer. So there are principally four energy. One is van der Waals force, van der Waals energy. Also, there is electrostatic energy. Okay. Okay. Just think of the bilayer. And there is van der Waals energy. Van der Waals energy, again, van der Waals energy is composed of actually one of the dipole, either dipole interaction, dipole in this dipole interaction, or in this dipole interaction. So, and there is some interaction. But in also bilayer, in the solution, when you think of a solution, there are many bilayers. Okay, so I'm talking about the interaction between the two bilayers. So they can be some van der Waals interaction. Also, there is some electrostatic interaction. Electrostatic interaction can be either attractive or repulsive. But van der Waals interaction energy is always attractive, right? And but there is the other energy, which is undulation energy. Also, there is a curvature energy. So, okay, in the solution, the diurnal solution, probably this single the lamellar layer, undulating lamellar layer, the layers are gonna affect each other, forming highly effect lamellar layer. But if the van der Waals dominates of this system, they form into they peg into some multi-lamellar phase, like the lamellar phase. But if the other repulsion force is overcome the van der Waals interaction force, this is can be equilibrium, forming to single like the vesicle phase. Okay, so for the structures, molecular interaction on the molecular energy point of view, I mean the shape is again very important, but also interaction here, the attractive energy, repulsion energy is very important to stabilize the surfactant structure in aqueous system. Okay, usually they are very competitive. Van der Waals energy dominates. They fade into like a multi-lamellar vesicle or something lamellar, multi-lamellar phase. And if the electrostatic can control, they can be individual like the vesicle phase. Or undulation is kind of the repulsion force. Okay, I will show you. And the curvature is kind of also the diffusion. So they are both competing each other, like van der Waals electrostatic and undulation and curvature. So you know very well the van der Waals and electrostatic. So van der Waals is just like that. And but undulation energy. I can use actually mic.
Will this maybe a cell phone or something else? Do you have a cell phone?
Yes.
Can you turn it on?
Okay. And Helfrich defined the undulation energy like this. Undulation energy is a function of the is K. K is bending constant, is also D, and is function of the KBT. For typical phospholipid, like that, K undulation energy is order of 10 to 40 kBT, which is relatively high. For microemulsion and highly swollen lamellar phase, is undulation energy, K, the bending constant is relatively small. So, and then what is undulation interaction can be understood like this way. If there is a two combining layers here, and this is the bilayer. One bilayer is combined by two walls. The undulation repulsion energy is defined by the collision force to the wall. That is kind of the physics of the physical concept of undulating energy. So which means that the layer is very, very flexible. It is highly undulating. Then there are undulation energy can be higher than the stiff layer. So like it is very, very flexible. It is very, very flexible inside here. So colliding, collision force to the wall is much, much higher. So which means that bending constant of this molecule is smaller. Okay, yeah, smaller. So if your molecule over here is very, very flexible, then it provides repulsion force further. So usually two bilayer want to peg each other based on van der Waals interaction force. But if this is very, very flexible, then they prohibit to attract each other, which is undulation repulsive force. So if the bending constant of this molecule is very, very low, then each bilayer can be individual instead of packing each other. Okay, that determines structure of the bilayer system. Okay, the other is the curvature energy. Curvature energy is also kind of the repulsive energy. So they competitive to van der Waals energy. So it's also function of the gain, spontaneous curvature and the bending constant and the K-bar play the modulus. So think of the unilamellar vesicles. Unilamellar vesicles have any particular spherical-like shape, even though there are the other shape also exists like a tube-like vesicle, something like that. Just think of unilamellar vesicles. But in order to be multilamellar vesicles, so the other bilayer has to be attached to each other based on van der Waals interaction force. However, when the other bilayer is attached to the one unilamellar vesicle phase, that spontaneous curvature is much, much changed. So when you see, okay. So actually that is dependent on the actual particular radius. So when you attach to the other molecule is attached to here, when you need some energy, constant energy for the curvature of that. So that again is kind of the against of the van der Waals interaction, and that forming something like unilamellar equilibrium unilamellar vesicles. So somehow van der Waals force and either electrostatic force and some undulation force and curvature energy has to be competitive with the attractive force. That have any particular system can be equilibrium. Okay, so then you have to understand behind of the So spontaneous monolayer curvature for single tail surfactants here, monolayer covers strongly from the spherical or rod-like micelle, something like that, they have any spontaneous curvature. Spontaneous curvature is actually no longer zero. And when you see the bilayer spontaneous curvature, two identical monolayer is combined each other, known as bilayer curvature, so which is just flat. Okay. For single component bilayer, single component bilayer, and this is symmetric bilayer, there is usually there is no spontaneous curvature. And but when you mix together surfactant system, the mixed surfactant can segregate inner and outer bilayer surface that lead to asymmetric bilayer, showing spontaneous bilayer curvature. Okay, that I think that makes sense, right? So that's kind of the stuff. And I will show you just some example of surfactant system. This is spherical. So cylindrical micelle is look like worm, and also kind of the amorphous polymer melts, something like that. But still, there are many arguments of the cylindrical micelle here, whether they are entangled or not. Frankly speaking, characterization of a surfactant system is not very easy. If you try to scattering methods, like the X-ray scattering or ultraviolet scattering, they give an average value instead of the individual structures. But they don't know whether that is cross-linked, or they don't know the other very different shape of surfactant exists or not. But they just know every structure, right? So this is figured by cryo-TM, okay, cryogenic TM. So cryogenic TM is not very old method. So even now, also there are many problems to use cryo-TM. So frankly speaking, nobody knows how many complex structures exist on a surfactant system. Still, we believe it. Okay, this is micelle phase, this is cylindrical phase, this is like the lamella phase, but we don't know. So they are combined each other. So that is a reality of the surfactant microstructures. Also, okay, this is a vesicle, the unilamellar vesicle bilayer, closed bilayer, and the multilamellar bilayer. Again, that is formed by fundamentally two parameters. One is molecular shape, either packing parameter or surface curvature augmenter, or the other is determined by molecular interaction. Okay, Van der Waals interaction or the whatever. Electrostatic, undulation energy, and the curvature energies all combined produce this kind of the equilibrium structures. So for multilamellar vesicles, generally they Van der Waals interaction a little dominates compared to the other diffusion force. That is the stack to each other. Also, there are many other surfactant phases. Still, we don't know. I mean, I think most of variety phase is in the surfactant. So lamellar phase, like L alpha phase, L beta phase, L Gale phase. There are many lamellar phases. I think for the lamellar phase, symmetric liquid crystal is most complicated. But probably in surfactant lamellar crystal system, most of the symmetric phase similar structure is comparable to the symmetric liquid crystal. And cylinder phase, double diamond phase is also IM3M, PM3M, space group, other space group, double gyroid, IA3D, something HPL, hexagonal perpendulated lamella, which is maybe the metastable state exists on surfactant system. And this is the lamellar phase. Lamellar phase when the water concentrated is increased. So because the water has a strong affinity with the polar group, that D layer spacing increase as a function of the water. So water going inside here, they make broaden of the distance like that. Hexagonal cubic phase, there are two hexagonal phase. H1 is two phase. This is hexagonal ray of infinite load like the micelle phase, and the strand mesh ribbon phase. That's almost the same as block component and other sample assembly. Okay, so if you understand the one molecular assembly system, you can understand the other molecular system as well. And find the composition between lamella and hexagonal usually, and the strand cubic P phase, D phase, G phase, phase IM, 3M, D is double diamond, P and 3M, G is something like that. Mesh and the ribbon is low. There are many phases. So just to think of the all of phase exists like seven crystal system, right? In a cubic, hexagonal, something like that. The rectangular, trigonal. So L3 phase, other L3 phase is isotropic sponge-like bicondyle phase. So that's no longer in positional order, and the spontaneous curvature is about 0, which is flat like that. And the L beta phase, the series Sapenia in UCSB, suggested this phase, and the lamella Gale phase, and also L alpha Gale phase, lamella Gale phase. Somebody suggests also LTV phase, entangled tubular phase. So there are many phases in surfactant system. Can I use it?
This one?
Yeah.
But you don't need to have a break, right? So,
Okay.
so maybe if you could finish in 2 minutes or so.
2 minutes?
2, 3, because it's time for the lunch break.
Okay.
Oh, up to 5 minutes.
Okay. So give me a signal. But however, as I told you before, surfactant is really complicated. When I see, actually this is the creative image I took when I was in the Santa Barbara. But what I observed in the image is that actually surfactant system is really complex. So, but even though when I believe it, okay, this is micelle phase, this is load-like micelle phase, but some system is crossover each other. And even though we think of this is micelle phase, some cylinder exists. This is from many the experimental the data. So I would say surfactant system is really complicated system. Okay. Also, in surfactants, there are the other system, polymer surfactant hybrid molecular assembly. So why we have to use polymer surfactant mixture, control rheology, also control stability of system. Also, this is an analogy between aqueous polymer surfactant mixture and the mixture of two discrete polymer. Okay. So many people study on this topic. I mean, system one includes the thermotropic liquid crystal with a polymer that's applied to PDLC, and the other person, the other investigator, is working on lysotropic liquid the crystal by incorporating epipelic polymer. So what happened? Also, the non-charged polymer and electrostatically stabilize the lamella phase, wholly electrolytes and electrostatically stabilize the lamella phase, and the polymer with the non-ion spectrum based on L alpha phase is also very interesting in this field. Also, the other investigator is working on the other surfactant system with epithelial polymer. Some people working on vesicle mixed with epithelial polymer, and the micelle, shielded micelle, hexagonal cubic, they do working on that. But particularly for vesicle polymer mixture system, it is really similar to our cell systems. For example, the biomembrane cell is, as you know, composed of lipid bilayer surfactant and some many types of the protein, which is polymer, is incorporated into this bilayer, which is a kind of the vesicle phase mixed with the polymer. So that's why the system is important to understand our cell membrane system. But the cell membrane is too complicated because even in our surfactants chemistry and physics, people working on is that they add one particular polymer, like a PEO, polyethylene oxide, into the vesicle bilayer. But our cell membrane contains really variety of the surfactant, lipid, different tail lengths of different types of the lipid, and also membrane has many kind of membrane exist. So still we have a long way to go to understand our cell membrane. But this is just the first step to understand our cell membrane. So I will stop here because it is lunch time. Maybe tomorrow we will explain more about the other application. Thank you.
Are there questions to this part of the lecture? Yes?
Okay.
Could you make me clear the difference between self-assembly and agglomeration?
Self-assembly and aggregation is similar. Yeah. Some people said self-aggregation. But the other people said self-assembly, self-organization. But they are still, similar. But however, particle aggregation maybe is different. Like self-assembly indicate that they have to give some spontaneous assembly and give some function, like making like a micelle phase or vesicle phase, something like that. But you have to make difference between aggregation. Particle aggregation maybe does not give function. Okay, if the particle is very assembled into cubic phase, that's self-aggregation or self-assembly. But just aggregation is aggregation. Okay, but you have to divide into both meaning. Okay. Okay.
More questions? If not, let us thank the speaker again. And we will meet here.